Welcome back to Sleepy Science Facts, where we drift into the mysteries of existence one calming fact at a time. Tonight, we're journeying into the universe, a place so vast and tranquil that even its biggest mysteries whisper rather than shout. In this soothing exploration, you'll learn how the universe began, what fills the silent space between the stars, and a few gentle cosmic secrets that might help your mind unwind. So settle in, breathe softly, and let the cosmos carry you into relaxation. Make sure to like, subscribe, and hit the bell for more sleepy science facts. And remember, read the first command for support. Imagine a darkness so vast, so silent, that it stretches beyond comprehension. In that emptiness, tiny sparks of light ignite, blazing across the void with energy billions of times greater than anything on Earth. Galaxies swirl in a cosmic dance, nebulae glow in vibrant colors, and stars are born, live, and die in spectacular brilliance. This is the universe, immense, mysterious, and endlessly beautiful. It is a story of creation and destruction, of unimaginable forces and delicate balances, spanning over 13 billion years and still unfolding. Every atom in your body was forged in the heart of a star. Every breath you take connects to processes that shaped distant worlds. The cosmos is not separate from us. It is the essence of our being, the stage upon which the drama of existence unfolds. Tonight, we embark on a journey through space and time, witnessing the universe not only as science describes it, but as poetry, as story, as awe-inspiring reality. We will traverse black holes and galaxies, witness the birth of stars, explore exoplanets, and glimpse the invisible forces that govern all of existence. Over 13 billion years ago, the universe as we know it did not exist. There was no space, no time, no stars, no galaxies, and no planets. Instead, all matter, energy, and potential were compressed into a singular point of infinite density, a state beyond comprehension. In an instant known as the Big Bang, this point expanded violently, setting into motion the unfolding of space and time. The universe, once a dimensionless, formless energy, began its journey towards structure, complexity, and life. In the first trillionth of a second, the universe experienced a period of exponential expansion called inflation, stretching faster than the speed of light. Tiny fluctuations in density, minuscule variations in energy, were magnified during this period. These fluctuations, invisible to the naked eye, would become the seeds for galaxies, clusters, and the vast cosmic web that we observe today. Within minutes, nuclear reactions forged the lightest elements: hydrogen, helium, and traces of lithium. These simple atoms formed a primordial soup, floating in an opaque, hot plasma. For nearly 380,000 years, the universe remained a dense, glowing fog. Photons, the particles of light, could not travel freely. They constantly scattered off electrons in a chaotic dance. But as the universe expanded and cooled, electrons combined with nuclei to form neutral atoms, allowing light to finally stream across space. This cosmic microwave background radiation, a faint afterglow of the Big Bang, can still be detected today, stretching across the sky in every direction. It is the universe's oldest light, a snapshot of the cosmos at its infancy, whispering the secrets of its birth to any who listen carefully. Gravity, the unseen sculptor of the cosmos, then began its work. Regions slightly denser than their surroundings attracted more matter, creating vast clouds of gas. Over millions of years, these clouds collapsed under their own gravity, forming the first generation of stars, gigantic, short-lived, and spectacularly bright. These stars burned furiously, fusing hydrogen into helium and, in some cases, forging heavier elements like carbon, oxygen, and iron. When these massive stars exhausted their fuel, they exploded as supernovae, scattering these elements across the surrounding space. Without these explosions, the universe would remain a landscape of hydrogen and helium, barren and lifeless. Instead, each star's death sowed the seeds for planets, oceans, and eventually life. The first galaxies formed as gravity gathered stars into bound systems. These early galaxies were small, irregular, and chaotic, yet they began the process of cosmic evolution. Galaxies collided and merged, stars were born and died, and over billions of years, increasingly complex structures emerged. The story of the universe is not static. It is a dynamic, unfolding narrative, written in light, matter, and gravity, spanning distances beyond comprehension and timescales far exceeding human imagination. In this cosmic dawn, the universe was a place of extremes: unimaginable temperatures, dense plasma, violent explosions, and yet also the first glimmers of order. The laws of physics, emerging from these early conditions, guided the formation of matter and energy. From this primordial chaos, the building blocks of everything, planets, galaxies, and life itself, were forged. The universe, in its infancy, was already writing the story that billions of years later would include our planet, our species, and our consciousness. As the universe matured, stars did not form in isolation. Gravity, the unseen sculptor of cosmic landscapes, pulled these newly ignited suns together into vast assemblies known as galaxies. These islands of stars, gas, and dust became the fundamental building blocks of the cosmos. Each galaxy is a city of light, containing millions to trillions of stars, yet separated from other galaxies by millions of light years of mostly empty space. To look at a galaxy is to gaze upon the history of creation itself, for every star within it has a story, a birth, a life, and often a violent death that echoes across the vastness of space. The earliest galaxies were small, irregular, and chaotic, mere fragments of the immense structures we see today. Observations from the Hubble Space Telescope reveal galaxies in their formative stages, swirling with clumps of gas, undergoing bursts of star formation, and colliding with neighboring proto-galaxies. Over billions of years, these collisions and mergers sculpted larger, more ordered galaxies, some forming majestic spirals like our own Milky Way, others becoming enormous elliptical galaxies containing billions of old, dying stars. The evolution of galaxies is a tale written over cosmic time, with gravity as the master author. Spiral galaxies, such as the Milky Way and Andromeda, are among the most visually striking. They contain a dense central bulge of older stars, surrounded by vast arms of gas, dust, and young, blue stars that swirl in intricate, elegant patterns. The arms are sites of active star formation, illuminated by newborn stars that heat surrounding gas into glowing clouds of hydrogen. Elliptical galaxies, in contrast, are more uniform, often spherical or elongated, composed mostly of older stars and little gas, signaling that their days of star formation have largely ended. Irregular galaxies defy structure, shaped by gravitational interactions and collisions, reminding us that the universe is as chaotic as it is beautiful. Beyond their visible matter, galaxies are dominated by dark matter, an invisible substance whose presence is inferred through gravitational effects. Stars at the edges of galaxies rotate far faster than expected based solely on the mass of visible matter, revealing the gravitational influence of dark matter halos surrounding each galaxy. This unseen mass provides the scaffolding for galaxy formation, guiding their shape, motion, and interactions. Without dark matter, galaxies like the Milky Way could not hold together. Stars would drift into the void, leaving a cosmos devoid of the structures we see today. Galaxies do not exist in isolation. They are part of larger structures, galaxy groups, clusters, and superclusters, bound together by gravity and interconnected in a vast cosmic web. The local group, for instance, contains over 50 galaxies, including the Milky Way and the Andromeda Galaxy. Beyond our local neighborhood, clusters like the Virgo cluster or the Coma cluster contain thousands of galaxies, their interactions shaping the evolution of the cosmos on scales far beyond human imagination. Collisions between galaxies are among the universe's most dramatic events. When two galaxies approach, their stars rarely collide due to the immense distances between them. Yet gravitational forces stretch, twist, and distort their shapes. Gas clouds collide, triggering furious bursts of star formation. Over millions of years, the galaxies merge into a single, larger entity, redistributing stars and gas, and sometimes feeding a central supermassive black hole. Observations of interacting galaxies, such as the Antennae galaxies or the Whirlpool galaxy with its companion, provide snapshots of these cosmic dances in action, showing us that galaxies are dynamic, living systems, constantly reshaped by forces on scales far beyond human comprehension. Within galaxies, stars, planets, and eventually life emerge. Nebulae, the glowing clouds of gas and dust, serve as stellar nurseries. Here, gravity pulls gas into dense pockets, igniting nuclear fusion and giving birth to new stars. These regions, such as the Orion Nebula or the Eagle Nebula's pillars of creation, are among the most visually stunning features of the cosmos. Yet they are also laboratories of physics, revealing the complex interplay of gravity, gas dynamics, magnetic fields, and radiation. In these clouds, the materials for future planets are forged, hinting at the universality of the processes that eventually led to worlds like our own. Galaxies are not just static collections of stars. They are living, evolving systems. Supernovae seed interstellar space with heavy elements, black holes regulate star formation, and dark matter shapes their gravitational potential. Observing galaxies allows us to trace the evolution of the universe, to see how structure emerges from chaos, and to understand the environments in which planets and life can form. Each galaxy is a testament to the forces that govern the cosmos, a monument to both creation and destruction, and a reminder that the universe is an interconnected, dynamic tapestry stretching across space and time. The Milky Way, our galactic home, contains hundreds of billions of stars, countless planets, and perhaps billions of habitable worlds yet undiscovered. From its central bulge to its sprawling spiral arms, it is a city of light in a dark ocean of space. Our solar system lies on one of its outer arms, orbiting the galactic center at nearly 828,000 kilometers per hour, completing a circuit every 225 million years. The stars we see at night are part of this enormous, rotating city of stars, and beyond them lie countless galaxies, each with its own story, its own history, and its own mysteries waiting to be discovered. Galaxies, in their myriad forms, reveal the scale, complexity, and beauty of the universe. They are the arenas in which stars are born and die, the homes of planets and the potential cradle of life, and the structures that make the cosmos intelligible to us. In studying galaxies, we glimpse the universe as it was, as it is, and as it will become, connecting us to a story that began billions of years before the Earth even existed. Every galaxy is a chapter in the grand narrative of the cosmos, and by observing them, we begin to understand the universe's past, present, and future. Stars are the universe's master craftsmen, forging the very elements that make planets, life, and everything we see around us. Born within the dark, dense clouds of interstellar gas and dust, stars ignite when gravity pulls enough material together to trigger nuclear fusion in their cores. This process converts hydrogen into helium, releasing an immense amount of energy as light and heat. From a distance, a star may seem like a simple point of light, but at its core, unimaginable pressures and temperatures transform matter, creating the building blocks of the cosmos. The life of a star depends primarily on its mass. Small stars, known as red dwarfs, burn slowly and steadily, lasting tens to hundreds of billions of years. They are faint, red, and resilient, outliving most other stars in the universe. Medium-sized stars, like our Sun, shine yellow and live for roughly 10 billion years. These stars maintain a delicate balance between gravity, which tries to collapse them, and the outward pressure from fusion, which keeps them stable. Massive stars, however, live fast and die spectacularly. Their intense gravity forces fusion to proceed rapidly, creating heavier elements like carbon, oxygen, silicon, and iron. These giants end their lives in cataclysmic supernova explosions, scattering enriched material across space, enriching future generations of stars and planets. The life cycle of a star is a story of creation, transformation, and sometimes destruction. In their cores, nuclear reactions fuse lighter elements into heavier ones, a process that cannot be replicated on Earth outside of the most advanced laboratories. These reactions generate the heat and light that make stars visible across billions of light years. Surrounding a young star, dust and gas coalesce into planets, asteroids, and comets, forming the architecture of planetary systems. Over millions of years, stars migrate, interact, and influence each other, their gravitational pull shaping the movement of gas, dust, and other stars. Stars also influence the universe on much larger scales. When massive stars die, they release shockwaves that trigger the formation of new stars in nearby clouds. Supernovae produce neutron stars or black holes, objects so dense that they bend space and time, influence galactic evolution, and even drive powerful jets of energy across the cosmos. These processes demonstrate that stars are not isolated actors. They are part of a larger cosmic ecosystem, interconnected and interdependent. Observing stars provides insight into the history of the universe. By measuring their composition, astronomers can trace back the generations of stellar evolution, uncovering the enrichment of elements over time. For example, population III stars, the first generation of stars, were massive, short-lived, and composed almost entirely of hydrogen and helium. Though none remain today, their existence is inferred from the chemical fingerprints in later generations of stars, showing how the early universe seeded the cosmos with the elements necessary for planets and life. Stars also give rise to some of the universe's most breathtaking phenomena. Nebulae, vast clouds of gas illuminated by starlight, glow with brilliant colors, their shapes sculpted by stellar winds, radiation, and gravity. The Orion Nebula, visible even to the naked eye, is a stellar nursery where new stars are born. The Eagle Nebula's pillars of creation, captured in stunning detail by the Hubble Space Telescope, reveal massive columns of gas and dust giving birth to hundreds of stars. In these regions, we see the universe in motion, a place of energy, creativity, and transformation on scales far beyond human comprehension. Stars are also crucial to the existence of life. The Sun, a relatively stable G-type star, provides Earth with light, heat, and energy that sustain ecosystems. Without stars, planets would remain frozen, lifeless spheres adrift in the dark. Moreover, elements like carbon, oxygen, nitrogen, and iron, essential to life, are products of stellar nucleosynthesis. Every atom in our bodies was once inside a star. When we gaze at the night sky, we are, in essence, looking into the furnaces from which we ourselves were forged. The diversity of stars across the universe is staggering. From tiny red dwarfs burning slowly for trillions of years, to massive blue giants shining with a brilliance 100,000 times greater than the sun, stars display a spectrum of color, size, temperature, and behavior. Some stars exist in binary or multiple systems, their interactions producing phenomena like eclipses, mass transfer, and even gravitational waves detectable across the cosmos. Others end their lives as supernovae, neutron stars, or black holes, each outcome reshaping the universe in profound ways. Ultimately, stars are the universe's engines of transformation. They take the simplest elements, hydrogen and helium, and forge everything else. They illuminate the cosmos, sculpt galaxies, enrich interstellar gas with life-essential elements, and create the conditions for planets and life to emerge. The story of stars is a story of interconnectedness, of cycles of birth and death that echo across billions of years. In understanding stars, we understand not only the cosmos, but also our own origins. Among the universe's most mysterious and powerful objects are black holes. They are the ultimate paradox, regions of space where gravity is so intense that nothing, not even light, can escape their grasp. Black holes are born from the deaths of massive stars, when the core collapses under its own weight, compressing matter into a singularity, a point of infinite density and zero volume. Surrounding this singularity is the event horizon, a boundary beyond which the laws of physics as we know them break down. Step across it, and there is no return. Yet, despite their darkness, black holes illuminate the cosmos in remarkable ways. Matter falling into a black hole forms an accretion disk, swirling at near light speeds, heated to millions of degrees. This process emits powerful X-rays, gamma rays, and other high-energy radiation, which can be detected across vast distances. Some black holes produce colossal jets of plasma that shoot into space, spanning thousands of light years, powered by magnetic fields twisted by the black hole's rotation. These jets can shape entire galaxies, influencing star formation and redistributing gas across interstellar space. Black holes are not all uniform. Stellar mass black holes, with a few to dozens of times the sun's mass, form from single massive stars. Intermediate mass black holes, whose existence is still being explored, weigh hundreds or thousands of solar masses and may reside in star clusters. Supermassive black holes, millions or billions of times the sun's mass, lie at the centers of galaxies, including our Milky Way. These cosmic giants anchor their galaxies, regulating star formation and influencing the motion of billions of stars. The Milky Way's central black hole, Sagittarius A, contains over 4 million solar masses and exerts a gravitational influence felt across the galaxy. Black holes are not only astrophysical objects, they are laboratories for physics itself. Their extreme gravity warps space and time, bending light, stretching matter, and even slowing time relative to distant observers. General relativity predicts these effects with astonishing accuracy, yet the singularity at a black hole's center remains a mystery, where quantum mechanics and relativity collide. Physicists ponder questions that may redefine our understanding of reality. Does information truly vanish inside a black hole, or is it preserved in subtle ways? Could black holes be gateways to other regions of spacetime, or even other universes? These enigmas make black holes one of the most exciting frontiers in modern science. Observational breakthroughs have brought black holes from theoretical curiosities to tangible realities. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow in the galaxy M87, revealing a glowing ring of superheated gas surrounding the invisible singularity. This milestone confirmed predictions from Einstein's theory of general relativity and offered a glimpse of one of nature's most extreme phenomena. Observations of gravitational waves from colliding black holes, detected by LIGO and Virgo observatories, have opened a new window into the universe, allowing us to hear the ripples in spacetime produced by these cosmic titans. Black holes also demonstrate the interconnectedness of cosmic structures. When galaxies collide, their central black holes may merge, creating supermassive giants that dominate galactic cores. The energy released in these events can trigger starbursts, blow away gas, and reshape entire galaxies. Black holes, therefore, are not just destructive. They are architects of cosmic evolution, shaping the universe on scales far beyond our comprehension. Despite their fearsome reputation, black holes are not cosmic vacuums indiscriminately consuming everything around them. A star in a stable orbit around a black hole can remain unaffected for billions of years, just as the Earth orbits the Sun without spiraling inward. They are both destructive and precise, exerting influence according to the immutable laws of gravity. Black holes are a testament to the extremes of nature, regions where matter, energy, and spacetime interact in ways that defy intuition. They remind us that the universe is not a gentle, static place, but a dynamic realm of unimaginable forces. By studying black holes, we not only learn about stars and galaxies, but also confront fundamental questions about space, time, and the ultimate limits of knowledge. In the darkness of a black hole lies a profound light, the light of discovery, curiosity, and the human desire to understand the cosmos. When massive stars reach the end of their lives, not all collapse into black holes. Stars with masses between about 8 and 20 times that of the Sun undergo spectacular supernova explosions, but their cores survive the collapse. These cores compress matter to densities unimaginable on Earth, forming neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons. In these stellar remnants, gravity and quantum physics collide, creating a state of matter that cannot be reproduced in any laboratory on Earth. Neutron stars are the ultimate expression of compactness and precision. Their radii are only about 10–15 kilometers, yet they contain more mass than our Sun. This incredible density means that a neutron star is essentially a giant atomic nucleus, held together by gravity and neutron degeneracy pressure. At their surface, gravity is immense, curving spacetime and generating extreme tides that would stretch any object beyond recognition. Magnetic fields can be trillions of times stronger than Earth's, accelerating charged particles to near light speeds and producing spectacular electromagnetic phenomena. Among neutron stars, a remarkable subset are pulsars. These are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, the beams sweep across space like a cosmic lighthouse, producing regular pulses detectable by radio telescopes on Earth. Some pulsars rotate hundreds of times per second, their precision so reliable that they rival atomic clocks. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, revealing a new and unexpected kind of celestial object. Pulsars have since become invaluable tools for astronomers, allowing the study of gravity, the interstellar medium, and even testing Einstein's theory of general relativity in extreme conditions. Neutron stars are laboratories of extremes. Their interiors may contain exotic forms of matter, such as superfluid neutrons, hyperons, or even free quarks. The collisions of neutron stars, observed through both electromagnetic and gravitational waves, produce heavy elements like gold and platinum, enriching the universe and seeding planets with the building blocks for life. The 2017 detection of a neutron star merger, GW170817, confirmed decades of theoretical predictions and marked a milestone in multi-messenger astronomy, combining gravitational wave data with optical, X-ray, and gamma-ray observations. Pulsars and neutron stars also reveal the interconnectedness of cosmic processes. They can exist in binary systems with other stars, transferring mass, accelerating particles, and sometimes collapsing into black holes. Magnetars, a rare class of neutron stars with ultra-strong magnetic fields, release enormous bursts of X-rays and gamma rays, demonstrating the extremes of energy the universe can produce. Their behavior challenges our understanding of physics, pushing the boundaries of what is possible in the natural world. Despite their incredible density and extreme conditions, neutron stars and pulsars are observable from millions of light years away. Radio telescopes detect their pulses, X-ray observatories reveal their hot surfaces, and gravitational wave detectors sense their violent mergers. In these objects, we see the universe's capacity for precision, energy, and transformation. They are both relics of stellar death and creators of cosmic renewal, forging elements, shaping galaxies, and providing insight into the laws of nature under conditions far beyond human experience. Neutron stars remind us that the universe is not uniform. It is a place of extremes, variety, and wonder. From the massive, luminous giants that explode as supernovae to the compact remnants spinning as pulsars, stars follow life cycles that drive the chemistry, dynamics, and evolution of the cosmos. By studying neutron stars, we explore the frontier where gravity, nuclear physics, and quantum mechanics converge, gaining a deeper understanding of the universe and our place within it. While stars dominate the night sky, it is around them that planets form, the smaller, quieter companions that harbor the potential for life. Planetary formation begins within protoplanetary disks, vast, rotating clouds of gas and dust encircling newborn stars. Within these disks, dust grains collide, stick together, and grow into planetesimals, tiny building blocks that over millions of years coalesce into planets. Gravity, the sculptor of celestial architecture, guides this process, pulling material together while the star at the center emits radiation that shapes the disk's structure. Our own solar system provides a textbook example. Around 4.6 billion years ago, the sun formed at the center of a rotating cloud of gas and dust. Within this disk, particles collided to form planetesimals, which merged into protoplanets. The inner regions, hotter and denser, produced rocky planets like Mercury, Venus, Earth, and Mars. The outer regions, rich in gas and ices, formed gas giants like Jupiter and Saturn, and ice giants like Uranus and Neptune. Collisions between protoplanets and leftover debris were violent, shaping planetary surfaces, triggering differentiation into cores, mantles, and crusts, and ultimately delivering water and organic molecules that would be crucial for life. Beyond our solar system, the discovery of exoplanets, planets orbiting other stars, has revolutionized our understanding of planetary formation. The first confirmed detection in 1992 revealed planets orbiting a pulsar, an unusual and extreme environment. Soon after, planets were discovered around sun-like stars, confirming that planet formation is a common cosmic process. Today, astronomers have identified thousands of exoplanets, ranging from Earth-sized rocky worlds to gas giants larger than Jupiter. Some orbit perilously close to their stars, scorched by intense radiation, while others drift in the habitable zone, where liquid water could exist. The diversity of planetary systems has challenged previous assumptions. Many exoplanets orbit their stars in eccentric, elongated paths, while others are hot Jupiters, massive gas giants hugging their stars in orbits far tighter than Mercury's. These discoveries suggest that planetary migration, gravitational interactions, and chaotic collisions shape planetary systems in ways we are only beginning to understand. Observations from space telescopes like Kepler and TESS, combined with ground-based studies, allow astronomers to characterize exoplanets. Sizes, masses, orbital dynamics, and even atmospheric composition, providing unprecedented insight into the universality and variety of planetary formation. Planetary formation is also intrinsically linked to stellar evolution. The chemical composition of a star influences the types of planets that form around it. Stars rich in heavy elements are more likely to host rocky planets, while those with abundant gases may form massive gas giants. Supernovae and neutron star mergers enrich interstellar clouds with heavy elements like carbon, oxygen, and iron, providing the raw materials for future planets. In this way, stars and planets are intimately connected, forming a cosmic cycle in which stellar evolution begets planetary systems, and planetary systems may, in turn, host life. Exoplanet studies are not just an academic exercise. They touch on the most profound question humanity has ever asked. Are we alone? By examining planets orbiting other stars, we begin to understand the conditions necessary for life. Planets with atmospheres, liquid water, and suitable temperatures may be common, and the chemical fingerprints of life, oxygen, methane, or other biosignatures, could be detectable in the coming decades. The search for habitable exoplanets connects astrophysics, chemistry, biology, and planetary science, bridging the gap between cosmic phenomena and the possibility of extraterrestrial life. Some exoplanets challenge imagination with extreme conditions. Super-Earths, rocky worlds larger than Earth, may have crushing gravity and thick atmospheres. Ocean worlds may be entirely covered in deep global seas, while lava worlds are molten from tidal heating. Yet these extremes also provide laboratories for understanding planetary physics and atmospheric chemistry. Each newly discovered planet expands our conception of what is possible in the cosmos, reminding us that the universe is far stranger and more creative than we ever imagined. Even within our own solar system, planetary moons reveal astonishing variety. Europa, a moon of Jupiter, harbors a subsurface ocean beneath its icy crust. Titan, Saturn's largest moon, has rivers and lakes of liquid methane. Enceladus ejects water geysers into space, hinting at hydrothermal activity beneath its icy shell. These worlds demonstrate that planetary systems are not confined to stars. They include moons, rings, and smaller bodies, each contributing to the complex dynamics and potential for life in a system. Planet formation is therefore a story of matter, energy, and time. From dust grains in a protoplanetary disk to complex worlds capable of sustaining life, the process is shaped by gravity, chemistry, radiation, and cosmic chance. Planets are born from stars, shaped by collisions, enriched by stellar explosions, and influenced by the invisible hand of dark matter. They are both ordinary and extraordinary, common yet capable of harboring unique and remarkable conditions. The study of planetary formation and exoplanets not only illuminates our origins, but also expands our imagination, revealing the boundless creativity of the universe. As the universe matured, galaxies did not exist in isolation. Instead, gravity drew them together into vast collections called galaxy clusters, the largest gravitationally bound structures in the cosmos. These clusters can contain hundreds or even thousands of galaxies, interacting in a complex gravitational ballet over millions of light years. The Virgo cluster, Coma cluster, and the more distant Abell clusters are examples of these cosmic metropolises, each a city of galaxies bound together by an invisible scaffolding, dark matter. Galaxy clusters reveal the universe's intricate large-scale structure, often referred to as the cosmic web. This web is a network of filaments, walls, and voids, stretching across billions of light years. Dark matter forms the backbone of this web, its gravity guiding galaxies into dense nodes while leaving vast empty voids in between. Observations from large surveys, such as the Sloan Digital Sky Survey, SDSS, map the positions of millions of galaxies, unveiling the universe as a colossal spiderweb of matter. It is within these intersections, dense cluster cores, that galaxies collide, merge, and evolve at accelerated rates. The environment within galaxy clusters is extreme. Galaxies in close proximity interact gravitationally, triggering bursts of star formation or stripping gas away entirely in a process called RAM pressure stripping. Hot intracluster gas, millions of degrees in temperature, permeates the space between galaxies, glowing in X-ray light and influencing star formation and galaxy evolution. Within these clusters, galaxies live dynamic lives, constantly shaped by their neighbors and the larger cosmic environment. Galaxy clusters are also laboratories for studying dark matter. By observing the motions of galaxies within a cluster and the bending of light from background objects, a phenomenon called gravitational lensing, astronomers can infer the presence and distribution of dark matter. These studies reveal that visible matter accounts for only a fraction of a cluster's mass, with dark matter dominating the gravitational landscape. Without this invisible scaffolding, galaxy clusters could not form, and the large-scale structure of the universe would be entirely different. Clusters can collide on titanic scales. When two clusters merge, shock waves ripple through the intracluster gas, triggering star formation and accelerating particles to near-light speeds. One famous example is the Bullet cluster, whose collision provides compelling evidence for dark matter, as the visible matter and gravitational mass are displaced, demonstrating the separation of normal and dark matter during such cosmic events. These collisions are not destructive in the everyday sense. They are transformative, shaping galaxies, distributing elements, and altering the structure of the cosmic web itself. Beyond clusters, filaments of galaxies connect the universe like strands of a giant spider web. These filaments channel matter, guiding galaxies and gas into clusters and shaping the universe's evolution. Observations using radio, X-ray, and optical telescopes reveal diffuse gas and magnetic fields along these filaments, highlighting that even the space between galaxies is alive with dynamic processes. Dark matter dominates these structures, yet ordinary matter, energized and illuminated, traces the underlying framework, revealing the beauty and complexity of the universe's architecture. The cosmic web is also central to understanding galaxy evolution. Galaxies in dense nodes often have older stars, little gas, and reduced star formation, while those in filaments or voids may continue forming stars and evolving more slowly. Interactions, mergers, and accretion along filaments contribute to the growth of galaxies and clusters, demonstrating that environment is a key factor in cosmic evolution. Each galaxy's history is intertwined with the larger structures it inhabits, connecting the microcosm of stellar life with the macrocosm of cosmic architecture. Galaxy clusters and the cosmic web are not just static structures. They are dynamic, evolving over billions of years. They expand with the universe, collide, merge, and interact, shaping the fate of galaxies and the distribution of matter. Within these structures, the universe demonstrates both order and chaos, elegance and violence, revealing the fundamental forces that govern cosmic evolution. Observing these vast structures reminds us of our place in the cosmos. Earth resides in a relatively quiet corner of the Milky Way, which itself is part of the local group, connected to the Virgo supercluster, which is a node in the immense cosmic web. From our tiny vantage point, we glimpse the grand tapestry of galaxies, clusters, and filaments, understanding that the universe is interconnected on scales far beyond our imagination. The cosmic web is the architecture of the universe, a vast and intricate design stretching across billions of light years, yet shaped by the same laws of physics that govern the atoms within our bodies. Galaxy clusters and the cosmic web reveal the universe's beauty, complexity, and interconnectedness. They show us that matter, energy, and gravity act together to produce the magnificent structures we observe today. By studying them, we uncover not only the history of the universe, but also the processes that have led to the emergence of stars, planets, and life itself. These colossal structures are living monuments to the forces that shape reality, demonstrating that the universe, in all its vastness, is an interconnected, evolving masterpiece. From the birth of the universe in the Big Bang to the formation of stars, galaxies, and planets, the cosmos has been in constant motion, expanding and evolving over 13.8 billion years. But what lies ahead? What is the ultimate fate of the universe? This question has fascinated scientists, philosophers, and poets alike, driving humanity to explore the nature of space, time, and the forces that govern all existence. The key to understanding the universe's destiny lies in its expansion. Edwin Hubble's observations in the 1920s revealed that galaxies are moving away from us, with more distant galaxies receding faster, a discovery that confirmed that the universe is expanding. Initially, scientists assumed that the gravitational pull of matter would eventually slow, stop, and perhaps reverse this expansion, leading to scenarios like the Big Crunch, where the universe collapses back on itself. However, later observations challenged this expectation. In the late 1990s, astronomers studying distant supernovae discovered that the universe's expansion is accelerating, not slowing. This surprising revelation introduced the concept of dark energy, a mysterious force counteracting gravity on cosmic scales. Dark energy constitutes roughly 68% of the total energy content of the universe, dominating the cosmic dynamics. Its nature remains one of the greatest mysteries in physics, challenging our understanding of the cosmos and the fundamental laws that govern it. The presence of dark energy reshapes our predictions of the universe's fate. If dark energy remains constant, the universe will continue to expand indefinitely in a scenario known as the Big Freeze. Galaxies will drift ever farther apart, stars will exhaust their fuel, black holes will evaporate via Hawking radiation, and the cosmos will become a cold, dark, and desolate place. Over unimaginable timescales, matter itself may decay, leaving a near-empty universe, a hauntingly silent cosmos. Alternative scenarios, though less likely given current evidence, are equally intriguing. If dark energy were to increase over time, it could lead to a big rip, where the expansion accelerates so dramatically that galaxies, stars, planets, and even atoms are torn apart. Conversely, if dark energy weakens or reverses, the universe could collapse in a big crunch, potentially followed by another Big Bang in a cyclic pattern. Each of these fates underscores the profound interplay between gravity, dark energy, and cosmic evolution. The fate of the universe is also intertwined with the life cycles of stars and galaxies. Star formation will eventually cease as gas is consumed or expelled, leaving galaxies dominated by long-lived, faint stars. Neutron stars, white dwarfs, and black holes will remain as remnants, drifting silently through the cold darkness of space. Cosmic radiation will redshift, becoming ever fainter, while the remaining structures, clusters, superclusters, and filaments will continue their slow expansion, fading into obscurity. Even in this remote future, the universe will continue to tell its story. Black holes will slowly evaporate through Hawking radiation, seeding space with subatomic particles. Protons themselves may decay over immense timescales, leaving only photons, neutrinos, and dark matter. The universe will reach a state of thermodynamic equilibrium, sometimes called the heat death, where no energy gradients exist to drive processes or sustain life. It is a sobering, awe-inspiring vision, highlighting both the fragility and the persistence of cosmic structures. Yet, amid this vast emptiness, there is beauty. The universe's destiny is not a sudden catastrophe, but a slow, graceful unfolding, a dance of matter and energy across incomprehensible timescales. Observing the cosmos today, we witness a universe in its prime, full of stars, galaxies, planets, and the potential for life. We are living at a moment when light, matter and energy are abundant, and the story of the universe is vibrant and ongoing. Studying the universe's fate is not merely an exercise in speculation. It drives our understanding of fundamental physics, from the properties of dark energy to the behavior of matter and gravity on cosmic scales. By mapping the distribution of galaxies, measuring the expansion rate, and observing the cosmic microwave background, scientists can refine models of the universe, connecting the distant past with the far future. Each observation brings us closer to answering questions that are at once profoundly scientific and deeply human. Where did we come from, and where are we going? In contemplating the fate of the universe, we also confront our own place within it. Human history spans mere millennia, yet we are capable of understanding processes unfolding over billions of years. The universe, in its immensity and complexity, becomes a mirror reflecting our curiosity, resilience, and desire to comprehend the cosmos. By studying the universe's destiny, we not only explore the physics of space and time, but also the profound philosophical and existential questions that have inspired thinkers for generations. The universe's fate is ultimately a story of transformation. From the fiery birth of the Big Bang to the gentle expansion driven by dark energy, the cosmos is in constant motion, evolving, reshaping, and revealing new mysteries. Its destiny reminds us that even in the vast emptiness of the far future, the universe is governed by the same elegant laws of physics that allowed galaxies, stars, planets, and life to emerge. It is a story of continuity, change, and the inexorable passage of time. A cosmic narrative in which we are fortunate observers, witnesses to the unfolding grandeur of existence. The story of the universe is not only one of stars, galaxies, and black holes, it is also a story of life. On at least one small, blue planet orbiting an unassuming star in the Milky Way, matter organized itself in a way that defied entropy, creating life. Earth, with its oceans, atmosphere, and magnetic field, became a cradle for this extraordinary phenomenon. From the first single-celled organisms to the explosion of biodiversity seen today, life is both a consequence of cosmic evolution and a profound testament to the universe's complexity and creativity. Life on Earth began more than 3.5 billion years ago in primordial oceans. Simple molecules combined to form self-replicating structures, eventually giving rise to cells, the basic units of life. Photosynthesis transformed the planet, producing oxygen and reshaping the atmosphere, paving the way for complex multicellular organisms. Over billions of years, life evolved in an intricate dance of adaptation, competition, and symbiosis, filling the planet with plants, animals, and countless microorganisms. Each evolutionary step was influenced by Earth's geology, climate, and chemical environment, demonstrating that life is deeply intertwined with planetary processes. Astrobiology, the study of life beyond Earth, extends this inquiry to the cosmos. Scientists consider what conditions are necessary for life: liquid water, energy sources, chemical building blocks, and stable environments. By studying extremophiles, organisms that thrive in Earth's harshest environments, from deep-sea hydrothermal vents to acidic hot springs, researchers gain insight into how life might exist elsewhere. These discoveries suggest that life is resilient and adaptable, capable of emerging in conditions previously thought uninhabitable. The search for life naturally turns to exoplanets. Thousands of worlds orbiting other stars have been discovered, some lying within the habitable zone, where temperatures allow liquid water to exist. Observatories like Kepler, TESS, and the James Webb Space Telescope have provided data on planetary atmospheres, compositions, and potential biosignatures. Future missions aim to detect molecules such as oxygen, methane, or water vapor, chemical fingerprints that might hint at life beyond Earth. These efforts bring humanity closer than ever to answering the profound question: are we alone in the universe? Life may not be evenly distributed. Some planets may host simple microbial life, while others could harbor complex ecosystems. Moons like Europa and Enceladus, with subsurface oceans, or Titan with its methane lakes, offer tantalizing possibilities. Even rogue planets, drifting through space without a star, may sustain life beneath thick ice layers, heated by internal radioactive decay or tidal forces. The universe, vast and varied, presents countless opportunities for life to emerge, challenging our imagination and expanding our understanding of biology, chemistry, and planetary science. The presence of life is also connected to stellar and planetary evolution. Stars forge the elements essential for life, supernovae scatter them across space, and planetary systems form from enriched clouds. Earth itself is a product of this cosmic cycle, containing elements created in the cores of stars billions of years before the sun existed. Life, therefore, is both a local phenomenon and a cosmic consequence, a continuation of the processes that shape stars, planets, and galaxies. Intelligent life, if it exists elsewhere, could offer profound insights into consciousness, culture, and technology. The search for extraterrestrial intelligence, SETI, uses radio telescopes to listen for signals from advanced civilizations, while planetary missions explore potential biosignatures within our solar system. The discovery of extraterrestrial life, even microbial, would transform humanity's understanding of its place in the cosmos, providing evidence that life is not a rare accident, but a natural outcome of the universe's evolution. Ultimately, the study of life in the universe bridges the microcosm and macrocosm. It connects chemistry and biology with astronomy and physics, showing how atoms forged in stars can organize into molecules, cells, and ecosystems. Life demonstrates the universe's capacity for complexity, resilience, and creativity, revealing that the same physical laws governing stars and galaxies also allow the emergence of consciousness, curiosity, and culture. By looking outward to the stars and inward at life on Earth, we witness a continuum of creation and possibility. Life is a reminder that the universe is not only vast and inhospitable, but also capable of producing astonishing order, diversity, and beauty. In understanding life, we understand the universe itself, a place where matter, energy, and chance converge to create not just stars and planets, but awareness, experience, and the enduring quest for meaning. As we gaze into the cosmos, much of what shapes the universe remains invisible. Ordinary matter, the stars, planets, gas, and dust that we can see, accounts for less than 5% of the universe's total energy content. The remaining 95% is composed of two enigmatic entities: dark matter and dark energy, phenomena that reveal the universe's hidden architecture and challenge our understanding of physics. Dark matter, first inferred in the 1930s by astronomer Fritz Zwicky, manifests through its gravitational influence. Galaxies rotate faster than visible matter alone can explain, and clusters of galaxies remain bound despite insufficient luminous mass. Gravitational lensing, where light bends around massive objects, further confirms dark matter's presence, tracing vast structures invisible to telescopes. Yet, despite decades of study, dark matter has eluded direct detection. It neither emits nor absorbs light, interacts weakly with normal matter, and remains one of the greatest unsolved mysteries in science. Cosmologists propose that dark matter is composed of exotic particles, such as WIMPs, weakly interacting massive particles, or axions, yet experiments have yet to confirm their existence. Its gravitational influence, however, is undeniable. Dark matter forms the scaffolding on which galaxies and clusters assemble, guiding the formation of the cosmic web. Without it, the universe would look entirely different. Stars and galaxies would be far less abundant, and cosmic structures as we know them would not exist. It is the invisible architect of cosmic evolution, silently shaping the universe over billions of years. Even more perplexing is dark energy, a mysterious force driving the accelerated expansion of the universe. Discovered in 1998 through observations of distant supernovae, dark energy constitutes approximately 68% of the universe's total energy content. Its nature is still unknown, but it acts as a repulsive force, counteracting gravity and stretching space itself. Dark energy determines the ultimate fate of the cosmos, influencing whether the universe will expand forever, rip apart, or undergo cyclic evolution. The interplay of dark matter and dark energy shapes galaxies, clusters, and the large-scale structure of the cosmos. Computer simulations incorporating these phenomena reproduce the observed distribution of galaxies, filaments, and voids, confirming that the invisible dominates the visible. Yet, despite its critical role, dark matter and dark energy remain fundamentally mysterious. They force us to confront the limitations of our knowledge, reminding us that much of the universe lies beyond perception and intuition. Observational programs continue to probe these cosmic mysteries. The Euclid mission, Vera C. Rubin Observatory, and the James Webb Space Telescope aim to map dark matter through gravitational lensing and study the effects of dark energy on galaxy evolution and cosmic expansion. Particle physics experiments seek to detect dark matter particles directly, using detectors deep underground or in space. Each approach is a testament to human ingenuity, uniting astronomy, cosmology, and physics in the quest to understand what governs the universe. Dark matter and dark energy also have philosophical implications. They reveal a universe that is far stranger than the one our senses perceive, dominated by invisible forces that dictate the formation of galaxies, the motion of stars, and the destiny of the cosmos. They challenge our assumptions about matter, energy, and the fundamental nature of reality, inviting humanity to rethink its place in an unseen and powerful universe. By studying these cosmic enigmas, we glimpse the limits of knowledge and the frontiers of discovery. Dark matter and dark energy remind us that the universe is not a static backdrop, but a dynamic, mysterious, and interconnected system. They reveal that what we see, the stars, galaxies, and planets, is only a fraction of reality, hinting at the immense, invisible structures that govern cosmic evolution. In contemplating these mysteries, we also witness the human spirit in pursuit of understanding. The search for dark matter and dark energy is not merely a scientific endeavor. It is a testament to curiosity, imagination, and perseverance. Each experiment, observation and simulation brings us closer to unraveling the hidden forces of the cosmos. And while the ultimate answers remain elusive, the journey itself illuminates the profound complexity, beauty, and majesty of the universe. Dark matter and dark energy are reminders that the universe is far more intricate than it appears. They challenge the mind, inspire exploration, and reveal the unseen architecture that shapes existence. In embracing these mysteries, we confront both the limitations and the potential of human understanding, discovering that the cosmos is a boundless, evolving, and astonishingly beautiful realm. Time is not merely a sequence of moments measured by clocks. It is a dimension interwoven with space, forming the very fabric of the universe. Albert Einstein's revolutionary theories of relativity revealed that space and time are not absolute, but dynamic, malleable, and intertwined. The universe is a four-dimensional continuum, space-time, where matter and energy dictate curvature and curvature dictates motion. In this cosmic dance, gravity is not a force in the traditional sense, but the manifestation of space-time curvature. Einstein's special relativity, proposed in 1905, showed that time is relative, flowing differently depending on velocity. Clocks aboard fast-moving spacecraft tick more slowly relative to stationary observers, a phenomenon confirmed by particle accelerators and GPS satellites. Space itself is similarly flexible. Lengths contract at high speeds, and mass increases as objects approach the speed of light. These effects, while negligible in everyday life, dominate the behavior of stars, black holes, and high-energy particles, reshaping our understanding of motion and causality. Building on this, general relativity, introduced in 1915, described gravity as the curvature of spacetime caused by mass and energy. Massive objects, like stars and black holes, warp the surrounding fabric, bending the paths of nearby objects and even light itself. This phenomenon, known as gravitational lensing, allows astronomers to observe galaxies behind massive clusters and map the distribution of dark matter. General relativity transformed physics, unifying space, time, and gravity into a single framework, and providing the foundation for modern cosmology. One of the most profound consequences of relativity is the prediction of gravitational waves, ripples in spacetime produced by accelerating masses. These waves remained theoretical until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the merger of two black holes, confirming Einstein's prediction a century later. Gravitational waves open a new window into the cosmos, allowing astronomers to hear cataclysmic events like neutron star collisions and black hole mergers, complementing traditional electromagnetic observations. Each detection adds a layer of understanding to cosmic evolution, revealing phenomena invisible through light alone. Relativity also redefines our understanding of the cosmos, origin, and fate. The Big Bang itself can be described as an expansion of spacetime, not an explosion in pre-existing space. Cosmic inflation, a rapid expansion in the universe's earliest moments, smoothed and shaped spacetime, seeding the large-scale structure we observe today. Black holes, singularities where spacetime curvature becomes infinite, push our understanding to the limits, where general relativity and quantum mechanics converge in ways we do not yet fully comprehend. Time and relativity also influence life in subtle ways. On Earth, the curvature of spacetime caused by our planet's mass requires GPS satellites to account for both special and general relativity, or their positions would drift by kilometers each day. In extreme environments, near black holes or neutron stars, time dilation becomes dramatic, slowing time relative to distant observers. Science fiction often imagines the human experience near such objects, but these effects are real, measured, and test the very nature of causality and existence. The fabric of the cosmos is not static, it evolves. As the universe expands, as galaxies collide, as black holes merge, space-time itself stretches, ripples, and bends. Relativity links the microcosm of atomic particles to the macrocosm of galaxies, connecting the motion of electrons to the evolution of the universe. It frames our understanding of gravity, motion, energy, and time, revealing that the cosmos is far more fluid and interconnected than our senses suggest. Through relativity, we also confront profound philosophical questions. Time is not universal. It is local and relative. Space is curved and dynamic. The universe is alive with motion, energy, and transformation, where past, present, and future are woven into a continuous, malleable fabric. Human perception is limited, yet through mathematics, observation, and imagination, we glimpse the deeper nature of reality. Relativity challenges intuition, expands our understanding, and offers a cosmic perspective that is both humbling and awe-inspiring. Space-time, relativity, and gravitational waves collectively illuminate the universe's inner workings. They reveal that reality is not fixed, but shaped by matter, energy, and motion. They show that the cosmos is a living, evolving entity, where stars, galaxies, and black holes dance within a flexible framework. Understanding the fabric of the universe is not merely a scientific pursuit. It is a journey into the nature of existence itself, linking the human mind to the vast, dynamic cosmos. Relativity teaches us that the universe is both stranger and more beautiful than we imagined. Time bends, space curves, and energy flows across the cosmos in ways that defy everyday experience. Yet, through observation, mathematics, and imagination, humanity can perceive these truths, connecting our brief existence on Earth to the eternal rhythm of the universe. In studying the fabric of space-time, we do more than explore physics. We explore our place in an immense, evolving, and astonishingly intricate cosmos. Black holes are among the most mysterious and captivating objects in the universe. They are the ultimate expression of gravity's power, regions of space-time where matter is compressed to such extreme density that nothing, not even light, can escape. Their existence was first predicted by Einstein's general relativity, but for decades they remained theoretical curiosities. Today, we have direct and indirect evidence for black holes, from stellar remnants in our galaxy to the supermassive giants at the hearts of galaxies. A black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. In stars exceeding roughly 20 times the mass of the Sun, the collapse is unstoppable. The core contracts to a singularity, a point of infinite density, while the outer layers may explode in a supernova, scattering enriched elements into space. The boundary surrounding the singularity is known as the event horizon, the point of no return. Beyond this invisible surface, all paths lead inward. Escape is impossible. Black holes come in various sizes. Stellar mass black holes, formed from individual stars, typically range from a few to tens of solar masses. Intermediate mass black holes, rarer and more mysterious, weigh hundreds to thousands of solar masses. At the center of nearly every galaxy lies a supermassive black hole, millions or even billions of times the mass of the Sun. The Milky Way hosts Sagittarius A, a supermassive black hole weighing about 4 million solar masses, influencing the orbits of nearby stars and shaping the galaxy's core dynamics. Despite their name, black holes are not entirely invisible. Material falling into a black hole forms an accretion disk, where gravitational energy heats gas to millions of degrees, emitting intense radiation, particularly in X-rays. Relativistic jets, powered by magnetic fields and rotation, can blast material across thousands of light years, shaping galaxy evolution and influencing star formation. Observations from telescopes such as Chandra, XMM Newton, and the Event Horizon Telescope reveal these energetic processes, allowing us to see the influence of black holes on their surroundings. One of the most astonishing achievements in recent astrophysics is the imaging of a black hole's shadow, first captured in 2019 by the Event Horizon Telescope. This historic image of the supermassive black hole in M87 revealed the glowing ring of hot gas circling the event horizon, providing direct visual evidence of these enigmatic objects and confirming decades of theoretical predictions. The image is both a triumph of human ingenuity and a profound reminder of the universe's extremes. Black holes are also laboratories for fundamental physics. Near the event horizon, space-time curvature is extreme, allowing tests of general relativity under conditions impossible to replicate on Earth. Hawking radiation, a theoretical quantum effect predicted by Stephen Hawking, suggests that black holes can slowly lose mass and evaporate over immense timescales, linking gravity, quantum mechanics, and thermodynamics in a profound cosmic interplay. Each discovery challenges our understanding, hinting at deeper connections between the fundamental forces of nature. Beyond individual black holes, their collective influence shapes galaxies and clusters. Supermassive black holes regulate star formation through energetic feedback, sculpting galactic cores and influencing cosmic evolution. Colliding galaxies often merge their central black holes, producing gravitational waves detectable across billions of light years. These cosmic mergers are both violent and transformative, demonstrating that black holes are not merely destructive voids, but active agents in the universe's grand narrative. Black holes also capture the human imagination. They embody paradoxes, extremes, and mysteries, points where known physics breaks down, horizons beyond which information seems lost, and singularities where density becomes infinite. They challenge intuition, confront us with the limits of knowledge, and inspire both scientific inquiry and philosophical reflection. In literature, film, and culture, black holes symbolize the unknown, the infinite, and the sublime, connecting scientific discovery with the human spirit. Yet black holes are not merely cosmic monsters. They are integral to the universe's life cycle. By recycling matter, influencing star formation, and shaping galaxies, they play a critical role in cosmic evolution. They remind us that extremes, chaos, and mystery coexist with order, beauty, and creation. Black holes reveal that the universe is not only vast and complex, but also deeply interconnected, where even the most destructive forces contribute to the grand tapestry of existence. In contemplating black holes, we confront the limits of space, time, and knowledge. They are reminders of the universe's power, its mysteries, and the boundless frontier that lies beyond observation. By studying these abyssal objects, humanity glimpses the extraordinary, the unimaginable, and the sublime. a cosmos where gravity reigns supreme, shaping reality in ways that continue to astonish, challenge, and inspire. The universe is vast not only in space, but in time. Its history spans 13.8 billion years, a scale almost incomprehensible to human perception. To understand the cosmos, we must consider these cosmic time scales, where the birth and death of stars, the formation of galaxies, and the evolution of planets unfold over millions and billions of years. Stars, in particular, are the engines of the universe, converting matter into energy, forging elements, and shaping the destiny of galaxies and life itself. Stars are born within nebulae, immense clouds of gas and dust. Gravity draws material together, forming dense regions called protostars. As the protostar contracts, pressure and temperature rise, eventually igniting nuclear fusion in the core. Hydrogen fuses into helium, releasing energy that balances gravity, and the star enters the main sequence, the stable phase that lasts millions to billions of years depending on its mass. Our Sun, a medium-sized star, has existed for about 4.6 billion years and will continue for another 5 billion years before evolving into a red giant. Stellar mass dictates a star's destiny. Small stars, less than half the Sun's mass, burn slowly, living trillions of years. Massive stars, tens or hundreds of times the Sun's mass, burn fuel rapidly and die young in mere millions of years. When massive stars exhaust their nuclear fuel, they collapse in supernova explosions, releasing tremendous energy and scattering heavy elements into space. These elements, carbon, oxygen, iron, and beyond, seed future generations of stars, planets, and ultimately, life. Supernovae are both destructive and creative, demonstrating that endings in the cosmos often lead to new beginnings. The remnants of stars vary according to their mass. Small stars leave behind white dwarfs, slowly cooling stellar cores composed mostly of carbon and oxygen. Massive stars may collapse into neutron stars, incredibly dense objects where a teaspoon of material weighs billions of tons, or into black holes, regions of space-time from which nothing can escape. Binary systems, where two stars orbit each other, produce even more exotic phenomena, such as X-ray binaries, pulsars, and gravitational wave-emitting mergers. These remnants are laboratories for extreme physics, allowing us to test the laws of matter, energy, and gravity under conditions impossible on Earth. Stars also govern the rhythm of galaxies. Star formation occurs in spiral arms, where density waves compress gas and trigger new stellar generations. Stellar feedback, winds, radiation, and supernovae shapes the interstellar medium, regulating future star formation and influencing the evolution of the host galaxy. Clusters of stars form, disperse, and dissolve over time, contributing to the dynamic life cycle of galaxies. The interplay between stars, gas, and gravity drives cosmic evolution, revealing a universe in constant transformation. Cosmic time scales also frame our understanding of planets and life. Stars provide energy, stability, and the elements necessary for planetary formation. The habitable zone, the region around a star where liquid water can exist, depends on the star's luminosity and lifetime. On Earth, the Sun has provided stable conditions for billions of years, allowing life to emerge, evolve, and diversify. Across the universe, stars of different types and ages create diverse environments, some conducive to life, others hostile. Understanding these time scales allows us to place Earth and humanity within the broader cosmic narrative. Observational astronomy allows us to trace stellar evolution across time. By studying star clusters of different ages, astronomers piece together the life cycles of stars, from birth to death. Spectroscopy reveals chemical composition, mass, temperature, and age, while telescopes spanning the electromagnetic spectrum detect phenomena from radio waves to gamma rays. Through these observations, we construct a cosmic timeline, connecting events across billions of years and vast distances. The life cycle of stars is also a story of cosmic alchemy. In stellar cores, simple hydrogen is transformed into helium and progressively heavier elements through fusion. Supernovae distribute these elements, enriching the interstellar medium and enabling the formation of rocky planets and the chemical foundation for life. Every atom in our bodies, every molecule essential to life, was once forged in a star. We are, as Carl Sagan famously said, made of star stuff, intimately connected to the cosmos through time and matter. Cosmic time scales remind us of our fleeting existence. Human life is measured in decades, civilizations in centuries, yet the universe operates on scales that dwarf imagination. Stars live, die, and reshape galaxies over millions and billions of years. Light from distant galaxies travels for billions of years before reaching our telescopes, allowing us to peer into the past and witness events long before Earth existed. Time in the cosmos is both vast and humbling, framing our understanding of life, death, and the unfolding story of the universe. By studying stellar evolution and cosmic time scales, we not only understand stars and galaxies, but also the conditions that allow life to arise, planets to form, and civilizations to flourish. Stars are the engines of creation, the clocks of cosmic history, and the beacons that illuminate the universe's grandeur. In tracing their life cycles, we trace the history of matter, energy, and life itself, connecting humanity to the vast, intricate, and ever-evolving cosmos. Nebulae are among the universe's most enchanting and essential structures. These vast clouds of gas and dust, often spanning hundreds of light years, serve as the birthplaces of stars and the chemical factories that enrich galaxies. To gaze upon a nebula is to witness a cosmic nursery, where matter coalesces, ignites, and gives rise to the luminous engines of the universe. Their stunning colors and intricate shapes, captured by telescopes like Hubble and the James Webb Space Telescope, reveal both beauty and the complex physics governing the cosmos. Nebulae come in many forms, each with a unique role in the cosmic life cycle. Emission nebulae glow brightly as their gases are energized by nearby young, hot stars, producing vivid red, green, and blue hues. The Orion Nebula, one of the most famous examples, showcases thousands of forming stars within a single cloud, some destined to become massive, luminous stars, others smaller companions like our Sun. Reflection nebulae, by contrast, shine not by their own energy but by reflecting the light of nearby stars, revealing the intricate patterns of cosmic dust. Dark nebulae, dense and cold, obscure light from objects behind them, serving as the incubators where protostars quietly form. Star formation within nebulae begins when regions of the cloud collapse under gravity. Small fluctuations in density trigger protostellar cores, which attract surrounding gas and dust. As the material accumulates, the core heats up, and once nuclear fusion ignites, a star is born. Surrounding gas and dust may form protoplanetary disks, the precursors to planets, moons, asteroids, and comets. Nebulae, therefore, are not just star factories. They are the genesis of planetary systems, the chemical crucibles that make life possible. Nebulae are also chemical laboratories. Elements forged in previous generations of stars, expelled by supernovae, enrich nebulae with carbon, oxygen, nitrogen, and iron. These elements mix with primordial hydrogen and helium, creating complex molecules, some even organic, which can be incorporated into forming planets. The study of nebular chemistry provides clues to the origins of life, revealing how simple atoms can assemble into molecules that ultimately participate in biological processes. Some nebulae are remnants of stellar death. Supernova remnants, like the Crab Nebula, showcase the aftermath of massive stars that exploded, dispersing their enriched material across space. These nebulae not only seed future generations of stars and planets, but also produce shock waves that compress surrounding gas, triggering new rounds of star formation. In this way, the universe sustains a cosmic recycling process, where creation and destruction coexist in a dynamic balance. Observations of nebulae provide insights across the electromagnetic spectrum. Infrared telescopes penetrate dense dust clouds, revealing hidden protostars. X-ray observations detect high-energy processes in supernova remnants. Radio telescopes map cold molecular gas, tracing the raw material from which stars are born. Each wavelength unveils a different aspect of nebular life, allowing astronomers to understand the physical processes that drive star and planet formation. Nebulae are also time capsules. Light from distant nebulae can take thousands of years to reach Earth, showing us snapshots of cosmic history. By studying nebulae in other galaxies, astronomers learn about the star formation rates, chemical evolution, and galactic dynamics across cosmic time. Nebulae, in this sense, are both laboratories and archives, revealing the past and present processes shaping the universe. Beyond their scientific significance, nebulae captivate the imagination. Their shapes, pillars, bubbles, filaments, appear almost sculpted, and their colors evoke wonder and awe. The Eagle Nebula's pillars of creation, for example, are iconic, showcasing towering columns of gas where stars are being born. These images bridge science and art, demonstrating that the universe is not only governed by physics, but also capable of inspiring profound human emotion. In essence, nebulae are the cradles of cosmic creation. They transform diffuse gas into stars, planets, and ultimately the conditions necessary for life. They are dynamic, ever-changing, and interconnected with the broader life cycle of the universe. From the quiet collapse of protostars to the violent explosions of dying stars, nebulae embody the processes that sustain cosmic evolution. In studying them, humanity glimpses the fundamental mechanics of the cosmos and the exquisite beauty of creation in its earliest, most formative stages. Nebulae remind us that the universe is not static. It is a living, evolving system where matter is constantly cycling, energy flows, and new structures emerge. They connect the death of stars to the birth of new worlds, the distribution of elements to the potential for life, and the laws of physics to the poetry of cosmic forms. By exploring nebulae, we explore the origins of stars, planets, and the very matter that constitutes life itself, a journey into the heart of the universe's creative power. Galaxies are the grand islands of matter scattered across the vast cosmic ocean. Each galaxy is a sprawling collection of billions to trillions of stars, gas, dust, and dark matter, bound together by gravity and evolving over billions of years. They are the fundamental building blocks of the universe, shaping cosmic structure, star formation, and the environments in which planets and life can emerge. To observe a galaxy is to glimpse a miniature universe, where creation, destruction, and transformation occur on scales that dwarf human comprehension. Galaxies come in a remarkable variety of shapes and sizes. Spiral galaxies, like our Milky Way, feature rotating disks, spiral arms, and central bulges, often hosting star formation along the arms and older stars in the core. Elliptical galaxies, in contrast, are more spheroidal, containing older stars and little gas, representing a more evolved stage in galactic life. Irregular galaxies defy classification, often shaped by collisions, interactions, or gravitational disturbances. Each type of galaxy tells a story of formation, evolution, and cosmic history. The formation of galaxies begins in the early universe. Tiny fluctuations in the density of matter after the Big Bang caused regions to collapse under gravity, forming the first dark matter halos. Gas accumulated in these halos, cooled, and condensed, giving rise to the first stars and proto-galaxies. Over billions of years, these proto-galaxies merged, collided, and grew, forming the diverse population of galaxies we observe today. Galaxy formation is thus both hierarchical and dynamic, a continuous process shaped by gravity, gas dynamics, star formation, and cosmic expansion. Galaxies are not isolated. They interact and evolve through collisions, mergers, and tidal forces. When galaxies collide, stars rarely collide directly due to the vast distances between them, but gas clouds interact violently, triggering bursts of star formation. Supermassive black holes at galactic centers can also merge, releasing gravitational waves detectable across billions of light years. These interactions transform galaxies, reshaping their morphology, dynamics, and star formation history. In this way, galaxies are living systems, constantly evolving through both internal and external processes. The distribution of galaxies across the universe is not random. Observations reveal a cosmic web, a vast network of filaments and voids formed by dark matter. Galaxies cluster along these filaments, while enormous voids remain relatively empty. This large-scale structure reflects the influence of dark matter and dark energy, illustrating that galaxies are not merely islands, but part of an interconnected cosmic ecosystem. Mapping these structures allows astronomers to probe the universe's expansion, the nature of dark energy, and the distribution of matter over cosmic time. Galaxies are also chemical factories. Through nuclear fusion in stars, they produce heavy elements that enrich the interstellar medium. Supernovae distribute these elements, enabling the formation of planets, organic molecules, and potentially life. Observing the spectra of galaxies reveals their chemical composition, star formation rate, and evolutionary history. Young, star-forming galaxies shine brightly in ultraviolet light, while older, more evolved galaxies emit primarily in redder wavelengths, providing a cosmic chronometer of galactic evolution. The study of galaxies also illuminates the role of supermassive black holes. Almost every massive galaxy hosts a central black hole, influencing star formation, gas dynamics, and galactic evolution. Energetic outflows, jets, and radiation from these black holes regulate the growth of galaxies, preventing runaway star formation and shaping galactic cores. The interplay between black holes and their host galaxies demonstrates that even the largest structures in the universe are governed by both visible and invisible forces, connecting the microcosm of gravity to the macrocosm of galactic evolution. Observing galaxies across cosmic time allows astronomers to trace the history of the universe. Distant galaxies, whose light has traveled billions of years, reveal the early stages of galactic assembly, showing how structure emerged from the near-uniform cosmos of the Big Bang. Modern surveys, such as the Hubble Deep Field, capture thousands of galaxies in a single image, offering a visual record of the universe's history, from its youth to its present complexity. Galaxies are also sites of beauty and wonder. Their spirals, bars, and clusters form intricate, awe-inspiring structures. Nebulae, star clusters, and supernova remnants within galaxies illuminate the night with spectacular colors and patterns. These cosmic masterpieces are more than scientific objects. They evoke emotional and aesthetic responses, connecting human perception to the grandeur of the universe. In essence, galaxies are the stage on which the universe performs its ongoing drama. They are cradles of stars and planets, laboratories of chemistry, and engines of cosmic evolution. From the smallest dwarf galaxies to the grandest ellipticals, each is a testament to the power of gravity, the passage of time, and the interconnectedness of matter and energy. Studying galaxies allows humanity to understand its place in the universe, revealing the structures that govern cosmic evolution and the environments that ultimately enable life. Galaxies remind us that the universe is vast, dynamic, and interconnected. They illustrate that matter, energy, and time operate on scales far beyond human experience, yet through observation and imagination, we can perceive their intricate patterns and rhythms. Each galaxy, a luminous island in the cosmic ocean, carries the story of the universe within it, its past, present, and future woven into the tapestry of space and time. The universe is not a static tableau. It is a dynamic, ever-changing arena where matter and energy interact on unimaginable scales. Among the most dramatic and visually stunning events in the cosmos are cosmic collisions. From the graceful merging of galaxies to the violent death of stars, collisions shape the structure of the universe, trigger the birth of new stars, and influence the evolution of galaxies and planetary systems. To witness a cosmic collision is to observe the universe in motion, a ballet of gravity, energy, and time. Galactic collisions are among the most spectacular events in the universe. When two galaxies approach, gravitational forces distort their shapes, pulling stars into tidal tails, compressing gas clouds, and triggering bursts of star formation. Contrary to what one might imagine, individual stars rarely collide due to the vast distances separating them. Instead, the galaxy's gas, dust, and dark matter interact, reshaping both structures over hundreds of millions of years. These cosmic encounters transform galaxies, turning spirals into ellipticals, merging star clusters, and redistributing matter in ways that define the galactic landscape. The Milky Way itself is on a collision course with the neighboring Andromeda galaxy. In about 4 billion years, these two giants will collide in a slow, graceful merger, creating a new, massive elliptical galaxy. While the process may sound catastrophic, the vast distances between stars mean that solar systems, including our own, may survive the encounter largely intact. Nevertheless, the cosmic fireworks of starbursts and gravitational interactions will profoundly reshape the galaxy's structure, creating new environments for star formation and planetary evolution. Collisions are not limited to galaxies. Stars and their remnants also interact in dynamic and sometimes violent ways. Binary star systems, where two stars orbit each other, can exchange mass, triggering nova outbursts or forming compact objects like neutron stars. When massive stars collide or merge, they can produce exotic objects, including rapidly spinning pulsars or magnetars. Stellar collisions are rare but provide crucial laboratories for understanding extreme physics, from nuclear reactions to relativistic effects and the behavior of matter under extreme pressures. Supernovae and their remnants are another form of cosmic collision. When a massive star explodes, its shock wave collides with the surrounding interstellar medium, compressing gas, triggering new star formation, and distributing heavy elements essential for planets and life. These interactions exemplify the universe's recycling process, where destruction begets creation, and energy flows from one generation of stars to the next. Each supernova is both an ending and a beginning, a testament to the transformative power of cosmic collisions. On even larger scales, galaxy clusters collide in events that can span millions of light years. These collisions, governed by gravity and dark matter, can create spectacular phenomena, such as the bullet cluster, where galaxies pass through each other, while the hot gas interacts and emits X-rays. Observations of such collisions provide evidence for dark matter, revealing how it behaves differently from ordinary matter and shaping our understanding of the universe's composition and evolution. Cosmic collisions also have profound implications for planetary systems. Shock waves from nearby supernovae may compress gas in protoplanetary disks, influencing planet formation. Stellar encounters in dense star clusters can perturb orbits, potentially ejecting planets into interstellar space or altering their trajectories. Even at the scale of individual solar systems, collisions and gravitational interactions play a critical role in shaping the architecture of planetary systems. The energy released in cosmic collisions is staggering. From the release of gravitational potential energy during galaxy mergers to the nuclear fusion unleashed in supernovae, these events are among the most energetic in the universe. They generate intense radiation across the electromagnetic spectrum, from radio waves to gamma rays, and produce gravitational waves that ripple across space-time, allowing us to detect and study collisions billions of light years away. Collisions are also key to understanding the universe's evolution. Galaxies grow through mergers, clusters assemble through repeated collisions, and the cosmic web evolves as filaments interact. Star formation, chemical enrichment, and the distribution of dark matter are all influenced by collisions, making them central to the story of cosmic history. Observing these events provides insight into the mechanisms that drive structure formation, galaxy evolution, and the conditions that allow life to emerge on planets like Earth. Cosmic collisions remind us of the universe's dynamism. They illustrate that creation and destruction are intertwined, that energy and matter flow through a continuous cycle, and that change is an inherent property of the cosmos. While human existence is brief on cosmic time scales, collisions show us the forces shaping galaxies, stars, and planets over billions of years. They are a vivid demonstration that the universe is not static, but alive with motion, interaction, and transformation. In contemplating cosmic collisions, we witness the universe's power, beauty, and complexity. Galaxies collide, Stars explode and black holes merge. Yet from these dramatic events arise new structures, new stars, and new potential for life. Collisions are the engines of change in the cosmos, linking destruction to creation, chaos to order, and time to evolution. Through them, humanity gains insight into the forces that sculpt the universe, illuminating our place within a dynamic and ever-evolving cosmic story. The universe, as we perceive it through light and matter, tells only part of the cosmic story. Beyond the stars, galaxies, and nebulae that dazzle our telescopes lies an unseen majority, dark matter and dark energy. Together, they compose approximately 95% of the universe, yet their nature remains one of the deepest mysteries in science. To understand the cosmos, we must grapple not only with the visible, but with the invisible, uncovering the hidden forces that shape the structure, expansion, and fate of everything we know. Dark matter was first inferred through gravitational effects that could not be explained by visible matter alone. In the 1930s, astronomer Fritz Zwicky observed that galaxies in the Coma cluster moved far too quickly to be held together by the gravitational pull of their luminous stars. The calculations suggested the presence of vast amounts of unseen mass. Later, Vera Rubin's measurements of galactic rotation curves confirmed that stars at the outskirts of galaxies orbit faster than expected, implying a halo of invisible mass surrounding galaxies. This mysterious substance became known as dark matter. Unlike ordinary matter, dark matter does not emit, absorb, or reflect light. It interacts primarily through gravity, shaping the motion of stars, galaxies, and galaxy clusters. Its gravitational influence is essential for galaxy formation. Without dark matter, the universe's large-scale structures, filaments, clusters, and superclusters would not exist as we observe them. Simulations of cosmic evolution that include dark matter reproduce the observed distribution of galaxies, providing strong evidence for its existence, even if its composition remains elusive. The leading candidates for dark matter are WIMPs, weakly interacting massive particles, and axions, hypothetical particles that rarely interact with normal matter. Experiments deep underground in space and using particle colliders aim to detect dark matter directly, but so far, it remains invisible, a ghostly scaffolding holding galaxies together. Its presence is inferred only through gravitational effects, from the rotation of stars to the bending of light in gravitational lensing, where light from distant galaxies is distorted by invisible mass along its path. While dark matter binds galaxies, dark energy drives the universe apart. In 1998, observations of distant supernovae revealed that the expansion of the universe is accelerating, contrary to expectations that gravity should slow it. This unexpected force, dubbed dark energy, now appears to dominate the universe, comprising roughly 70% of its total energy density. Its nature is unknown, but it acts as a repulsive force, stretching space-time itself and determining the ultimate fate of the cosmos. The interplay of dark matter and dark energy shapes the universe's large-scale structure. Dark matter pulls matter together, forming clusters, filaments, and galaxies, while dark energy pushes space apart, driving cosmic acceleration. Together, they orchestrate the dance of the cosmos, balancing creation and expansion in a dynamic equilibrium that is both subtle and profound. Without these invisible forces, galaxies might never have formed, stars might never have ignited, and the universe would look vastly different from what we observe today. Dark matter and dark energy also challenge our understanding of fundamental physics. And that's where we'll pause for today. I hope you enjoyed this little long journey into the Milky Way. We'll continue the next part tomorrow, so make sure to come back, get comfortable, and drift into more sleepy science facts with us. Until then, rest well, stay curious, and I'll see you in the next episode.